First, we're going to go back and look at measures of relative standing and z-score. We'll do more of that a lot later, but I want to get started on this and describe that. So we want to look at if you have a mean and then you know a value compared to the mean, it could be population or sample, then how is that compared to everything else? And you need to know the standard deviation to figure that out. So like how far away is it from the mean? Okay, so z-score relative standing is called a z-score, and you just say z. So you say z is equal to the variable that you are in question. So you could do like body temperature, you could do height of something, weight of a car, there's an average, and then there you have a variable. So the variable is x minus, and usually we say x bar because you don't know the actual standard deviation. Actual, well, that too, but actual, you don't know the actual population. So this most of statistics is based off of sampling. Not all the time, but most of it. Okay, and then you divide by S. Again, all sample. So let's do an example. Kind of pertains to the quizzes. So let's look at this example. So quiz score. And let's say the average was 25 out of 35. So that would be like, you got 100 on the quiz, but forgot to turn in your work. Then you'd get 25. All right, so the max is 35. So, and it's given, so either calculator given. Now, and this is one of the main differences for this in a that I calculate all the time is your scores, because I have the full population. The population is the class, so I can use sigma and mu, but generally you still call it a sample of everyone's, so it's a little loose. Anyway, suppose the standard deviation was 4. All right, then your z-score, so you say z-score, although I'll leave that out from now on. Z-score is your 30 minus 25 divided by 4. Make sure you can do this calculation by hand. So it's 5 over 4, which is 1.25. So we say that 25 lies, the scores lie 1.25 standard deviations about the mean, so around the mean. So I'm not telling you your an actual score. I'm telling you what's the mean and what's the standard deviation. So what we know then is the scores on the exam lie 1.25, or this is how you say it, 1.25 standard deviations about or around the mean. So 30 is equal to x bar plus 1.25 times s. So so you're talking about basically it's like you're normalizing, and that's a word we will be using, but you're normalizing uh, the mean. So you're making it all within a certain range, and what we can this is how you can apply the empirical rule and things like that. So this is called the bell shape or normal curve. So bell shape or normal distribution. So the bell shape or normal distribution is something you're going to come across all the time. This is basically what's assumed for most data sets. Like when I say most, like 99% of data sets, you assume the distribution is normal. That's not always true, but that's what's assumed. So the distribution looks like this. This is your bell curve concept. I'll try to draw a picture. It's symmetric, even though I didn't quite draw it symmetric, but it's symmetric about the mean. Looks like that. I can't help but do the little tail, little arrows, because that's normally you don't see it like that, but that's how you draw asymptotes. So it's asymptotic as you approach that. The center is always your mean, so that's your x bar or your sigma. Sorry, I didn't mean to say that, did I? That's your x bar or mu, depending on population or sample. And then you go out. One standard deviation is here and here. So that would be, I'll just use x bar. That's x bar plus s. And this is right here, x bar minus s. And you go out again to here, and it's the same distance. You go out again is 2s, and then 3s, right? And what you are saying then is that all your information is in there. So all the data points lie inside that curve. Let's see if I can actually draw it. Okay, so everything's inside here. I mean, I can make it colorful, why not? All right, so all the information is in here. So it looks like area. I mean, that's kind of what you're assuming, and this is some of the nuances that we'll talk about. But it's like you're clumping the data, and you're saying it's all in here. And so that's the accumulation of the data. And the area, this is one of the key ideas because this is called a probability function. It's probability density function, which we're going to get to more carefully later. But the area under there is always equal to 1. And it looks kind of like that. It might be skewed one way or the other, but that's what we mean by probability density function. And that's what we're going to spend a lot of our time on. We talked about earlier the empirical guidelines, and let me draw the picture again. So if you have that one standard deviation, empirically, approximately 68% of your information is one standard deviation. And then you go out again to the outside, to the next standard deviation, you have 95%. So one side or the other, you'd be half of it, but the total, let's see, how am I going to say that? I'll just say that this and this. Okay, so you add those together, and you're good 95%. And then you do the outsides, everything in between as well, right? So it's a 68% plus those sides plus the next sides. And on the if you include 3 standard deviations away from the mean, then you have 98.7%. So if you're talking about, I don't have a very good way to describe that right now, sorry, but the description is pretty easy. You're looking at the number of responses, or the number of things, the number of samples that you find. most of the information is going to be 3 standard deviations away from the mean. Okay, so all of this information. Okay, so that's the major concept we want to get at. So we will be concerned about that. How far away from the mean is your sample? So you could think of it as medical trials, drug trials, stuff like that. You don't want very many, deaths, for example. So you want to be way out here, that only a tiny percent that may or may not have been the cause of that medicine is your sample when you use it, or is the result when you use it. So depending on the situation, and education is not as critical, so your error is going to be more in here. You don't need to be way out to 4 standard deviations away from the mean. Maybe you're okay with 2 standard deviations or 2.5 standard deviations, and we'll talk about what that means. So that's kind of where we're heading. So just a quick review of empirical rule again. You have 68% is x bar minus s. This would be an interval, x bar plus s. And then you have 95% is 2 standard deviations away from the mean, x bar minus 2s, 2x bar plus 2s, and that's literally an interval. And then 98.7% of information is x bar minus 3s, 2x bar plus 3s. Okay, so the z-score, and there's tables to this. I think I've already posted some of those in Canvas, or look to make sure it's there. And there's a bunch of tables, and it shows those represent the standard deviations. You'll see like 1.25, 1, 3, and we'll be looking stuff like that up. Okay. Now, let's talk about next. We're kind of getting at up here. So that was a little cleanup, little homework to some things that I may have missed that I didn't ask you about. Let's get on to discrete probability function. So now we're going to distinguish between looking at these curves and different probabilities, whether it's discrete or continuous. So we're going to specifically look at right now discrete probability functions, mean, expected value, standard deviation, and then we'll get into something more specific, which is the binomial probability, and then if we have time, the Poisson probability distribution. So first, let's talk about random variable. I don't like to do what I'm about to do, but I'm going to sometimes do this, cover things up, and then I'll undo it. So you can undo it by clicking on it, basically. So write that down. A variable is called a random variable. So now we'll get into the concept of random variables. If the value is chosen or done by chance. So we'll be describing the concept of random variables. So, and using the idea of random variables. So random variables are basically a chance situation. So pretty much everything we talked about was a random variable. So the number of times you flip a coin, that kind of stuff, rolling a die, all of that has to do with random variables. Those are random variables. It's a random situation, a random chance. It could be selecting things or sampling a population. That's random, right? How you do the sampling is random. That's a random variable. These are just more examples. Number of defective things, widgets, bolts, whatever. So the number of them is a random chance. So that's called a random variable. You could randomize how many people like blue cars. Again, you're doing a sample, and that's a random variable. So the nature of itself of sampling has to be random, and we call that a random variable. Okay, so you get the idea there. All right, so then we look at next the probability functions. So probability distributions. And really, that's kind of what we'll be looking at for a while, is just the different probability distributions. And first one we'll look at is discrete versus continuous, or we'll look at discrete and what that is. So, so probability distributions is really, we've already done this as well. We're just now naming it. Probability distributions, I'll just say like a table, chart, graph. Okay, and we call it P of X. So take our heads, tails, we end up with this chart. That's a probability distribution. Right? That in of itself is the sample space. Okay, so this is the requirements. Okay, so requirements. So requirements for a discrete probability distribution. And let's abbreviate that, PD, probability distribution. Otherwise, we'd be writing all day. So requirements for a discrete probability distribution. And I'm not going to get too much into all kinds of examples. Certain things, like, you just look it up if you're not sure. But discrete versus infinite. So infinite, we have this concept of it being non-ending. But we also have the concept of continuous. Like in algebra, we always talk about continuity and smooth curves and things like that. So simple idea, I'll just draw it up on here. So that's continuous. That's discrete, period. Continuity means everything in between. Discrete means individual clicks. Okay, it's like, it doesn't have to go approach infinity. That's not the idea. It's like, let's take a volume. Most volumes are actually continuous. You have an infinite range between values. You dial it up, and theoretically it's infinite. Sometimes old things are like, maybe you have clicks, and I don't know if it's old, something's nice. You have clicks. It goes click, 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 click. Those are discrete, right, on a volume deal. And then see what else is volume and discrete. So discrete things is you have one after the next. You count them. There's 1, here's 2, here's 3, here's 4. Okay, so we also call that countable. So because you can literally count them. All right, so that's the difference. Not going to get too much into those details after that. All right, so requirements for a discrete probability distribution, that the probability, so I'll say where P of X is the probability of X, so the probability that it occurred. So it could be the probability to flip 3 heads in a row, which we know is 0.5 times 0.5 times 0.5, because each flip is independent, and you flip it 3 times, and you just multiply them. So it's 1/8. Okay, so the probability of flipping 3 heads in a row is 1/8. That is a probability of X, whatever X may be. So that has to be between 0 and 1. So the probability, if it's 0, it cannot happen. If it's 1, it must happen. And then there's everything in between. Okay. And then the sum, if you add up all the probabilities, the sum of the probabilities must add up to 1. So if you're taking our coin flips, and feel free to go back and look at it, and you're doing heads, tails, I listed out, we did it together, right? So we listed out the heads, tails. If we do it 3 times, we listed out every possibility. It must be one of those possibilities. So the probability of any of those happening must be 1. Okay, so if you add them up, it must equal 1. That's a critical distinction and concept. All right, so, oops, too small. Okay, so must know those. Okay. So look at some examples. Okay, that's probably good right there. We'll look at expected value, mean, discrete, standard deviations, and things like that next.